In this section, we're going to finish up our combinations without repetitions by doing an applied problem, which will lead us to a theoretical result, which is called Vandermonde's identity. But really the focus is on the applied problem. So in this problem, there are 7 women and 9 men, and we want to select 5 to make a basketball team, and we need at least 1 man and one woman to be on that group of 5. And we're wondering how many ways are there to do this. Or really count the number of different teams. So that's our task. There's a couple ways of thinking about it. I'll present the way I originally thought of, and then I'll present the way I think the book does. But I'll make a connection between the two at the end, which when I saw it, I thought was pretty cool. So we need at least 1 man and 1 woman on the team. So what's not possible is like 0 man and then 4 women. Sorry, blanked out there. Oh, sorry, 0 man and 5 women. That's not possible. That's a no-go. And what's also not possible is all men and 0 women. So that's also no good. So I'm just going to start listing off the cases that would be good. So for example, we could have 1 man and 4 women. We could also have 2 men. If 2 men are on the team, then we have 3 women. If we have 3 men on the team, then we have 2 women. 4 men on the team, we have 1 woman. And we can't go any higher than that. Because if we went to 5 men and 0 women, then we'd end up in this situation. So those are really the 4 cases which we can do. So it then breaks down into counting each of these situations. And I know actually that each of these situations are disjoint, so in the end I'm just going to add these, right? If you're on a team with 1 woman and 1 man and 4 women, that's completely disjoint from any team with 2 men and 3 women. There's going to be no overlap there. So these are disjoint sets, so we can add them with the addition rule. So how can we count teams with 1 man and 4 women? Well, that means from the 9 men, there's 9 men here. From the 9 men, I'm going to choose 1 of them. And then my step 2 is to choose the woman. Well, there's 7 women, and I want to choose 4 of them. So that's the number of teams where there's 1 man and 4 women. Next up is this situation here. Again, I have 9 men. I'm going to choose 2 of them this time. And then from the woman, I have 7 women, and I'm going to choose 3. And then the next set, I have, again, 9 men, choose 3 this time. Once I've chosen my men, using the multiplication rule, I can choose my woman. 7 choose 2. And then lastly, the most men I can have on the team is 4. 9 choose 4 times I choose my woman. 7 choose 1. All right. And that would be my answer. And it turns out, again, I wouldn't calculate this by hand. This would be a great analytical answer, meaning just like you leave it as is. And that shows me the most information, really. It shows me that you counted in some way. If you want to get a numerical answer, I would just go to like Wolfram Alpha or something like that, some computational engine, and you're going to get 4,221 if you put that in. So that's the number of different teams. Number of 5-person teams chosen from 9 men, 7 women, where each team needs at least one man and one woman. All right, so that's one way of counting it. Well, let's count it a different way. I'm gonna go over the book's alternative solution, or I wouldn't say alternative. It was their solution that I saw, and then I'll actually make a connection. So the book's way of doing it, and I'm not sure why I didn't think of it, but it's a good way as well, is to really just count all, and then we're going to subtract ones we don't want, which is what we've done in some previous sections. It's kind of an inclusion-exclusion situation. So counting all, that's pretty simple. We have, remember, 9 men, 7 women, and we want a 5 combination. Well, all of them, then all possible teams would be 16 distinguishable people, right? N equals 16 distinguishable people, and I'm choosing 5 of them. So counting all of them, that's 16, choose 5. And what are the ones that we don't want? So I'll set it up in a way I've done before using some sort of inclusion-exclusion. I'm going to say let M set, that's the set of 5-person teams that have at least one man, and W set is going to be the same, but at least one woman. And so before we had this like Venn diagram situation. So this is M and this is W. And what we want is we want the teams where there's at least one man and one woman. So we're really after this intersection here. What are some things that are in this? So this section here that I'm going to highlight, this blue, is only men are on the team. So for example, M1, M2, M3, M7, and maybe M8. Maybe that's one team that's in there. And this section here in orange, that's only women. So for example, one such element could be like W1, W3, W4, W5, and we need one more, maybe W6. Okay, so that's a team that could be in there. We don't want the blue teams, we don't want the orange teams. We want the teams where there's an intersection between them, meaning they have at least one of each. So just like we've done before, we count all of them, and like I said above, this is 16, choose 5, and then we want to subtract the blue amount, and then we also want to subtract the orange amount. How many are only men? Well, remember there's 9 men and there's 7 women, and we want a K subcommittee or sub-team or a combination of 5. So that means the only men means you're choosing from those 9 distinguishable men objects, and 5 of them must be chosen. So that's how much the blue is. And then the orange similarly would be 7, choose 5. And if you do, again, a computational calculator, this would be your final answer, which would be acceptable to write. If you did a computational calculator, this would be 4,221. And so our two answers end up being the same. Right up here we had 4,221. Oops, that's weird. And then down here we had 4,221. What's interesting is kind of connecting these two. So notice that up here in this section, I wasn't allowed to have the n choose 5. Right? There's nowhere up here is the n choose 5. Look at all the n's, or the ones with the men. I'm not allowed to have the n choose 5. No, sorry, 9 choose 5. And I'm not allowed to have any with the 7 choose 5, right? This only goes 7, 1, 2, 3, and 4. And in other words, the total amount, 16 choose 5, is really equal to these plus the ones up here. All right, so I'll write that there. So the total number of 5-person teams is 16 choose 5. And that is equal to, well, we could do 9, 0. So this would be where there's 0 men and there's 5 women, or you could have a team where there's 1 man and 4 women. And so forth. Then we have, so that was 3 men here, then we have 4 men on the team, which would mean 1 woman. And then we have 5 men on the team, which means 0 women. So this section, these two here, sorry, I won't do that with that. This 9 choose 5 is this right here. Because 7 choose 0 is really just 1. And then the 7 choose 5 is this one right here, because remember 9 choose 0 is 1. And so what we just showed is that 16 choose 5 is equal to this sum. I'm going to write it in summation notation now. This is 16 choose 5 equals the sum, k equals 0 to, what is it, 5. 9 choose k, and 7 choose 5 minus k. All right. And this 16 choose 5, that can really be written as 9 plus 7 choose 5. And I'll just rewrite that sum on the left, on the right, sorry. And this right here is called Vandermonde's identity, which is one of the more famous identities that are around with the binomial coefficients. Don't quote me on it, but I think if it's like, I think in general, it could be m plus n choose k, or no. Always forget the general formula, but m plus n choose j equals k equals 0 to j, m choose k, n choose j minus k. I think so. Something like that. But in any case, I think it's best to work through these problems in an applied sense, get a better feeling for actual numbers, and then you get your general formulas as well. So if it interests you, look up Vandermonde's identity. It's famous in the combinatoric world. And otherwise, hopefully this problem gave you a good sense of how to do things flexibly, how to do things using different methods, and how to use counting with binomial coefficients. See you in the next video.